So now we'll generalize this 1D case that we just considered and instead look at a 3D volume that is moving. So let's consider a moving volume V of t. And it has some, so that's V of t is the volume, and it has some area A of t. And we are considering a small area segment here, dA, which has a unit vector associated with it, n dA, and the volume is moving at a velocity b. Yeah, b is the velocity at which this whole object is moving. So after some time dt, our area is going to change into a separate element, and that's associated with the whole change of the whole volume. So now we have V of t plus delta t, and there's an area associated with it, A of t plus delta t. The change in the volume, dV, can be written as the velocity b times delta t times n dA. So that is the change of volume in that small element that we've considered here. So it really is b dot n times delta t dA. So we're now considering what does the derivative of some function f look like in this field. So it's f function of x and t. Now x is a vector, used to be just the one-dimensional number x in the Leibniz theorem, but in the general case it's the vector x. And we're integrating now over the whole volume. And so that is given as the limit for delta t going to 0, 1 over delta t, and there's two components here, that's v plus, we're integrating v of t plus delta t, f of x at t plus delta t dv, and subtract f of x of t integral of dv v of t. So nothing new here yet, and we can Taylor expand r as now write f of x and t plus delta t as f of x and t plus delta t df dt, as we did earlier. And we can write delta v. We know that delta v is just v of t plus delta t minus v of t. So if we consider term A here, this is our first term, term A, then A becomes the limit of delta t going to 0, 1 over delta t, and it consists really of four terms. Integral of v, f of x t dv, plus the integral of delta v f of x t dv plus the integral of delta v delta t df dt dv plus the integral of v delta t df dt dv. And I don't know really why I started here with delta v and then v. Let me just switch these quickly. Yeah, so it's just expanding those two terms from here to here. Now, this term here, we can quickly see that this is a higher order term, right? This is of order delta t, delta v, so that's negligible. That's going to go to 0 faster than the other terms. Now, this term here is going to cancel with term b. Sorry, I should have clarified. Here's term b here. So this here cancels with b. So then we're just left with d by dt of f dv really is just the limit of delta t going to 0, 1 over delta t, integral delta v f of x t dv plus v delta t df dt dv. Now recall that we found that dv is n dot b delta t dA. So we can plug this in for dv into our equation here, and so we get the limit, just considering the first term, we get the limit delta t goes to 0, 1 over delta t, integral over delta v f of x and t n dot b delta t dA. And so our delta t here cancels with this delta t. And this term approximates an area integral over f of x and t times n dot b dA. In other words, as delta t goes to 0, the depth, in quotation marks, depth of the volume integral goes to 0, and we approach a surface integral over dA. Yes, over dA. So the general Leibniz theorem can be written as follows. It's the integral of d by dt of, it's the derivative of an integral, f dv, and it really is the integral of the change in f over the original volume over time, plus boundary term that's very much analogous to the boundary terms in the 1D Leibniz case. So now we're integrating the original f over the boundary a, and under the consideration of how fast a changes, and that's b dot n dA. That's essentially this term is the translation of the boundary a. So now let's consider a material volume V, i.e. now we consider that V is a material volume, meaning it moves with the flow. With the flow, no influx or outflux. In that case, then B, the velocity of the volume, is just U, is the flow velocity. And that allows us to state Reynolds' theorem. Reynolds transport theorem writes d by dt, and so that's the material derivative of an integral of the field f dv is equal to the change in f, the integral of the change of f over the original volume v, plus an integral over the area times fu dot dA. Page 4. So there's two physical interpretations of Reynolds' transport theorem. And the first one is the special case. If you consider f to be a constant, namely 1, then you can show that Reynolds' transport theorem actually reduces to this equation we had last time, which was 1 over v dv dt is just dui dxi, i.e. the trace of s. So I have, under f equals 1, the first term, so that this term, for f equals 1, the first term just becomes dv dt. This term obviously becomes 0, and this term, it can be shown, would be v times dui dxi. What that means is that the volume Vt is conserved as it moves with the flow. The second interpretation is that essentially the Reynolds transport theorem, Reynolds transport theorem is an extension of the material derivative for finite size volumes. And you can kind of see that these three terms here, so this. That these three terms are approximately equivalent to the analogous to, so this is the integral version, and then the analogous derivative version is df dt plus u dot grad.